Precise definition of a limit, part 3. Let's look at landing inside of error bounds for even more graphs. So just a reminder of how we use absolute value inequalities to describe distance, and how we use absolute value inequalities to describe error, which is very similar. It's just the distance between some value and f of x as opposed to some value and just x. Here we want to use the given graph of f of x is equal to the square root of x to find a number delta such that if 0 is less than the absolute value of x minus 4 is less than delta, then the absolute value of f of x minus 2 is less than 0.4. So here we're looking at the distance between x and 4 being less than delta, and when that distance is true, the distance between f of x and 2 will be less than 0.4. So let's take a look at our graph here to make sure it's actually representing what we want. So the distance between, well, we're centered at 2, which is good. And the distance between 2 and 2.4 is 0.4, just like we want. And the distance between 1.6 and 2 is also 0.4, just like we want. Now we need to find the distance between 4 and these bounds here, because we see that our error bands intersect with the function here and here, and we want to know the inputs that will land us within this band. So unlike some of the graphs we looked at before, this does not give us the x values. So we have to do a little more thinking here. So 1.6 and 2.4 are both outputs of the function y is equal to the square root of x. So that means we have that the square root of x is equal to 1.6. And then in order to solve for x, we'll have to square that 1.6. So that means we have 1.6 times 1.6, which is 2.56. So the input that lands us at 1.6 is 2.56. And then we have to do a similar thing to find the input that lands us at 2.4. So we have that the square root of x, our output, is equal to 2.4. So then we have to square both sides of this to get that x is equal to 2.4 squared. So that's 2.4 times 2.4, which is 5.76. So that is the input that lands us at 2.4. Now that we have the inputs that we need to check our distances. So we need to find the distance between 2.56 and 4, and 5.76 and 4. The distance between 2.56 and 4 is 1.44, and the distance between 4 and 5.76 is 1.76. And we just want to remember that we want to choose the smaller distance because that will still land us within our error band, or error bounds. But if we chose the larger distance, then our output would not land within those bounds. So for this particular scenario, we have that delta is equal to 1.44. So 1 44/100. And what's interesting about this is we can actually write the limit that this is sort of approaching as well, because our goal here is to be centered at 2 for f of x and centered at 4 for x. So we're looking at the limit as x approaches 4 of the square root of x, and we want that to be equal to 2. And we're sort of approximating it with these bands here. So we're hoping that as x approaches 4, f of x is approaching 2. And we know that that's the case anytime we're falling within these bounds at least. Graph and use the graph to find the number delta, such that if the absolute value of x minus pi over 4 is less than delta, so if the distance between x and pi over 4 is less than delta, then the absolute value of tangent x minus 1 is less than 0.2. So then the distance between tangent x and 1 is less than 0.2. So let's look at the pieces here. So this is our A, so that's the center for x. Tangent x is the function we're looking at. And 1 is the center for those error bounds, or the limit that we're approaching. So the limit that we're looking at here is the limit as x approaches pi over 4 of tangent x. And we're hoping that that will be equal to 1, or at least a maximum of 0.2 away from 1 when we're some distance delta from pi over 4. So we need to be able to graph delta to make a little more sense of this. Sorry, not graph delta, graph tangent x. So if you don't know how to graph tangent x, you probably want to make sure that you review that. So tangent x has, at least for this one piece of it that we're interested in, asymptotes at pi over 2 and at negative pi over 2. And that's just something you want to make sure you know. And then halfway between 0 and pi over 2 is pi over 4, which is also just something you want to know. And halfway between negative pi over 2 and 0 is negative pi over 4. And then in terms of points that you just want to know on this graph of tangent x, you want to know that there's a point at pi over 4, 1, and that there's a point at negative pi over 4, negative 1. And finally, that there's a point at 0, 0. And that negative 1 does not look like it's balanced. So I'm just going to redraw that real quick. That's a little better at least. And then our graph is somewhat looking like a curve. This, of course, isn't perfect, but it's a sketch that will help us make more sense of this problem. And it has the main key features of this area of tangent x that we're interested in. Okay, so we know that for our error band, we're centered at 1, and that the maximum distance away from 1 that we want to go is 0.2. So 1 plus 0.2 will give us 1.2, and 1 minus 0.2 will give us 0.8. And we have that distance, epsilon, or error epsilon, of 0.2. So that's good. So now we know what our error band looks like, or error bounds. And we're interested in finding the inputs that will land us within these bounds. So we'll have to figure that out. So just like before, when we had that square root of x as our function, we know that our outputs for tangent x are 0.8 and 1.2. So we can solve this. So we have tangent x is equal to 0.8. And that means, well, the inverse of tangent x, or the inverse of the tangent function, is arctangent. So we can take the arctangent of both sides of this equation. So we have the arctan of tangent x and the arctan of 0.8. And then, because arctangent and tangent are inverses, they will cancel out, and we have that x is equal to arctangent of 0.8. And that is one of our mysterious possible bands. Then we also have that tangent x is equal to 1.2. So again, we can take the arctan of both sides. So we have the arctan of tangent x is equal to the arctan of 1.2. Our arctan and tangent will cancel out on that side. So we get that x is equal to the arctangent of 1.2. Where'd my 1 go? And that is the other one of our mysterious bands. Unfortunately, unless you have a calculator or a computer, you're not going to be able to approximate this. So that means we're stuck. We want the minimum distance between these bounds and pi over 4, but since we don't know how big the arctan of 0.8 and the arctan of 1.2 are, we don't really know how big these distances are. So what we can do is use the wonderful math function min, which, as an example, which I'm going to write awkwardly in this corner, if you have the min of 1 and 3, the output would be the smaller number, which is 1. So we want the minimum distance. So we have the minimum of pi over 4 minus arctangent of 0.8. And that was this left bound, the distance here, which I guess is another question mark. So many questions. And then we have the other distance for our right bound, so that'll be the arctangent of 1.2 minus pi over 4. We're not really sure which one of these is smaller, but we definitely want the smaller one to be our delta. And if we had a calculator, such as if you're doing homework as opposed to if you're taking a quiz, you could actually figure out which one of these you need to use. For the limit as x approaches 3 of x minus 2 is equal to 1, find the largest possible values of delta that correspond to epsilon is equal to 0.2 and epsilon is equal to 0.1. So this is a two-part question. But for both parts, we can kind of figure out what's going on. So we have that our a is 3. Our f of x is x minus 2. And our L is 1. There isn't room to write a, but I can at least write the f of x in L. So we're trying to show that if the distance between x and 3 is less than some delta, then we'll land inside our error bound, so the distance between f of x, which in this case is x minus 2, and 1 will be less than whichever epsilon we're looking at the moment. So let's start with epsilon is equal to 0.2. And we'll need to sketch a quick graph. So we need to sketch a graph of x minus 2 and make sure that it includes 3. So 1, 2, 3, and we know this has been shifted down 2, and that we have a slope of 1, so there is a quick sketch of a graph of x minus 2. Doesn't have to be perfect. Okay, so we know that for our error, we're centered at 1. And the maximum distance from 1 in this case is 0.2. So we're looking at 1.2 and 0.8. as our error bounds here. And we want to find the inputs that will land us within these error bounds. So we're looking for what are the inputs so that we can find the distances. So we have that x minus 2 is equal to 0.8, which means that our first input is x is equal to 2.8. And we have that x minus 2 for our upper bound is 1.2. And that occurs when our input is x is equal to 3.2. And all I did here is add 2 to each side in order to solve for x. And then we can look for our distance delta. The distance between 2.8 and 3 is 0.2. The distance between 3 and 3.2 is also 0.2. So that's not too bad. We have that delta is equal to 0.2 for this particular case. Then let's take a look at our second scenario, which is where our epsilon or error is equal to 0.1. We'll just need to sketch our graph again. It's not going to be any prettier. I suspect it will even be uglier than last time. I'm just graphing my y-intercept and then using my slope of 1 to hastily sketch the next points. Okay, so we're still centered at 1 for our error, but now our bound is 0.1. So we're looking at 1.1 and 0.9 for our bands. This is very much not drawn to scale. And we're trying to figure out what are the x values that will land us within those bands. Let me do a little bit of a better job drawing these bands here. So we have that one of our bounds is where x minus 2 is equal to 0.9. And that will occur where x is equal to 2.9. And then we have that our lower bound, our upper bound is where x minus 2 is equal to 1.1, which occurs where x is equal to 3.1. And then we want to find our distances, which I did not leave enough room for. The distance between 2.9 and 3.1 is 0.1, and the distance between 3.1 and 1 is also 0.1. That got very, very messy looking. So we have that the delta that will land us within this error band is 0.1. So depending on what you choose for your epsilon, you'll need a different value for your delta. We want to use the given graph of f of x is equal to 1 over x to find a number delta that fulfills the following condition. If the absolute value of x minus 2 is less than delta, so the distance between x and 2 is less than delta, then the absolute value of 1 over x minus 0.5 is less than 0.2. So the distance between 1 over x and 0.5 is less than 0.2. So if we were to think about the limit that this is approaching, or representing, we have the limit as x approaches 2 of the function 1 over x is equal to, hopefully, 0.5. Let's take a look at this graph. So we see that our error bound is centered at 0.5, that limit that we're approaching, and we want the error, the distance away from 0.5, to be a maximum of 0.2, which is the case because 0.5 and 0.7 are 0.2 apart, and the same with 5/10 and 3/10. And this is interesting because we have fractions and decimals all mixed together in this representation. And we're trying to find the inputs that will lead us to be within this bound so that we can find the distance delta that will guarantee we land in those error bounds. So we need to find the distance between 10 over 7 and 2. So that means we have 2 minus 10 over 7, which will be the same as 14 over 7 minus 10 over 7, which is equal to 4 over 7. So 4/7 is that first possible delta. And then we also need the distance between 10 over 3 and 2. So that'll be 10 over 3 minus 2, which is the same as 6 over 3. And 10 over 3 minus 6 over 3 gives us 4 over 3. And we just want to choose the smaller number, which is 4 over 7. Because if we have a distance of 4 over 7, we make sure we land within those bounds. But if we have a distance of 4 over 3, we might end up with an output that is not within our bounds. So the delta we want to choose is the smaller of those two, which is 4/7. We want to use the given graph of f of x is equal to x squared to find a number delta that fulfills the following condition. If the absolute value of x minus 1 is less than delta, then the absolute value of x squared minus 1 will be less than 1/2. So if the distance between x and 1 is less than delta, then the distance between x squared and 1 is less than 1/2. So that means we're looking at the limit as x approaches 1, we want it to be centered at 1, of our function x squared is equal to, well, f of x is centered at 1. And we're hoping that we trap this limit here within bounds, where we're falling within 1/2 of 1. So 0.5 is equal to 1/2. If our input is less than some number from 1. So we need to find these inputs. So when our output is 0.5, we need to figure out what our input is. And when our output is 1.5, we need to figure out what our input is. So we know that our function x squared is equal to 0.5 for that lower bound. So we just need to solve that for x by taking the square root of both sides. So we have x is equal to plus or minus the square root of 0.5. And we're actually only interested in that positive square root because we're only interested in the right side of this parabola. The positive square root of 0.5, I wrote more equal signs, is about 0.707. And then we also know that for our upper bound, we have our output x squared is equal to 1.5. So we'll solve for x by taking the square root. So we have x is equal to plus or minus the square root of 1.5. Again, right now we're only concerned with the positive square root, which is equal to about 1.224. So now we have our inputs. And we need to find the distance between each of these input bounds so we can figure out which delta we need to use. The distance between 0.707 and 1 is 0.293, and you just get that from doing 1 minus 0.707. And the distance between 1 and 1.224 is 0.224. And we just want to take the smaller distance, which is that 0.224. So delta is equal to 224 thousandths. That's 0.224. 0.224. So as long as we're inside that band, we know that we're guaranteed to land within our error bounds as well.